Hello everyone. The topic of today's presentation is Introduction to Digital Communication. Well, let us start with the discussion on model of a communication system. The what happens is the input message comes from a source. Uh, the the input message is then converted using a transducer into a signal. The transducer can be a thermostat or it can be a mic. So then it goes as an input signal, has to be transmitted using a transmitter, right? So the transmitter, this is a very general block diagram. I'm at the very superficial level of a communication system. So the transmitter transmits the transmitted signal. We call it as a transmitted signal. The signal passes through the channel. It may be any type of channel, maybe a wireless or a wired channel. Then the signal is received at the receiver, right? And from the receiver, the signal is fed to an output transducer. For example, if it is a audio, if it is an audio signal or a speech signal, then it may be the output transducer can be a speaker. So it then converts into the output message. So this is the most important point that is required to be mentioned here is that the channel introduces distortion and noise. Because of this, the reception at the receiver end becomes difficult, and we have to the whole problem of communication system is to estimate what was transmitted from the transmitter side. So at the receiver, we need to make an estimate of what signal was transmitted, because the channel is random and it introduces distortion and noise, and because of these two factors, the reception can be difficult. So various methods, various techniques have been developed so that the what was transmitted, we can estimate that signal to perfection. I mean, not perfection, but to nearest to the perfection levels. Right now, now let us understand what is distortion. So distortion is any deformation or alteration of the signal due to traveling in the channel. So examples can be attenuation or expansion in the signal width. Now, for example, this is the bit stream 011, 01, 00, and 1. And we transmit these bits in the form of waveforms. For 0, it is a negative voltage, maybe minus 5 volt or whatever the designer chooses. And for 1, it can be plus 5 volt, right? So when this becomes the transmitted signal or transmitted waveform. When this waveform travels through the channel, what happens? Uh, Signal at a distance, at a certain distance d, so they starts occurring the distortion, and the because this dotted line shows the actual transmitted waveform, but when it goes through the channel, so there starts occurring the attenuation, the signal level starts decreasing, and you also see that the signal starts expanding and spilling over into the neighboring bits, right? So signal at a more distance, at a distance twice what is this, what is the second waveform. Now in the third waveform, what you see is more attenuation has occurred and more spreading of the signal into the neighboring bits has occurred. Now because these are these two factors, what we call are termed as the distortion in this signal. Now, noise attenuation is a reduction in the strength of a signal due to loss of energy while passing through different materials, and is measured as attenuation per unit distance. Right. Noise is another factor. Noise is an undesirable signal and is random, and we have to estimate the noise probabilistically, and we have to actually take the the expected values of noise. But when we will come to the mathematical analysis, then I will explain at that point that how the noise calculations are done. Noise is an undesirable signal and is random, and it is really unpredictable, right? So if this is the signal which has traveled through the channel, so the signal is now actually signal with noise, right? And if we take out the noise on the floor, so this is known as the noise floor, where the noise is if the noise is extracted from the signal, you will see that there is a disturbance, there is a random disturbance which is occurring in the signal which has traveled through the channel, right? Now, the examples of noise can be interference from other signals transmitted on nearby channels. It can be automobile ignition radiation or some other sources. With proper care, this type of noise can be minimized or eliminated. So this type of noise is known as the external noise, the environmental noise. Now, there can be noise present in the signal due to internal factors. Those internal factors can be thermal motion of electrons in conductors, which we call as the Brownian motion, right? Then random emission of electrons, other sources inside the electronic devices, right? So the effect of internal noise can be reduced but can never be eliminated. With proper care, the external noise can be minimized, or to a great level it can be eliminated also. Now, another important factor in the communication system is the signal to noise ratio. Noise is a major factor that limits the speed of communication. To study the efficiency of a communication process, right, how the communication system that has been designed, how what are the performance levels of that system, we need to analyze the noise signal, right? Signal to noise ratio is a factor that is used for this purpose. So signal to noise ratio is the ratio of the signal power to the noise power, right? As distance of communication increases, the signal power decreases due to distortion and noise, right? And because the signal, if you look at the ratio of SNR, it is the ratio of the signal power to the noise power. Now the signal power decreases due to distortion, and noise power increases due to accumulation of noise. So ultimately what happens is the signal to noise ratio decreases while the signal is traveling through a distance. So in that case, we have to make an estimate of, we have to design methods to increase the signal to noise ratio which is received at the receiver, so that we can at least get a level of the signal, level of the SNR, so that we can estimate the transmitted signal. Now, the amplification of the received signal to make up for the attenuation is not helpful. If we think that we can amplify the signal, but that will not help, because that will also amplify the noise, because the noise will also be amplified in the same proportion and the signal to noise ratio remains the same. So that is a factor. If we try to increase the signal levels by a factor m with amplification, the noise levels will also be increased by the same factor. In that case, the signal to noise ratio remains the same, which is our metric to judge the performance of the communication system, right? So the amplification will not help. We will have to devise other methods and techniques to to improve the signal to noise ratio. Now, the information that, or what we call as the signal, it can be of various forms. It can be a message. The message can be again analog or digital. The message can be the temperature readings from a certain transducer, the voice message, or some kind of image, etc. That we have to send it through the communication system. The digital form of the message can be English text, which can be A, B, C, D, and so on, because that is a digital form. And it can also be a teletype message, Morse coded text. Actually, Morse code was developed in 1837 And this is treated to be the first digital communication system which came into existence in 1837. Right. So this is a digital form of the message. Now the signal can be of two types, analog and digital. This is a continuous form of the signal, right? And digital can be represented with a waveform, right? And these can be bits 0, 1, and so on. And the bits can be represented using a waveform. So that we call as a digital signal. Data is digital only, it cannot be analog. So data is actually the presence of zeros and ones, right? So these are known as the bits, and these we call as the binary. So this becomes the data. So there are three types of information that we are discussing at present. One is message, the other is signal. The signal can be of this form in the analog domain, and it can be represented using a waveform in the digital form. Actually, this representation, this in the digital domain, this representation actually is for the representation of the bits only, right? Okay, so because there is a certain voltage level, positive voltage level, which can represent 1, and the lower voltage levels can represent 0. This we will treat it as a baseband modulation. I will cover these topics when we discuss the baseband modulation and the low pass equivalent of the systems and the signals. Now, this is the graphical representation of various types of signals. This is analog and continuous, digital and continuous, analog and discrete, right? And this is digital and discrete. Okay. Now, this is a very important aspect of digital communication, which says that why do we go for the digital communication instead of the analog communication? So let us look at the reasons for using a digital communication system, and let us look at what is noise immunity. Now, this is the distorted signal which is received at the receiver. So this distortion has occurred due to channel, right? So distorted noisy signal, if you if you will see a little closely, you will see that there are ripples present in the waveform. So this is actually a distorted signal. We are making distinction between distortion and noise. So this is distortion, which is distorting the waveform of the transmitted signal, right? So there is an attenuation, and there is expansion of the waveform into the neighboring. There is a distortion, attenuation, and expansion of the waveform, and the effect is spilling over to the next to the neighboring bits, right? And this is actually distortion with noise, and distortion is of course there. And if you will see closely, you will see that there are ripples, there are ripples present in the periphery of these waveforms. These are actually the this represents the noise, ripples from addition of noise, right? So if this is on the positive side, and this waveform is on the negative side, the data can be recovered correctly as long as distortion and the noise are within limits. Now the point is that if the noise limits are not very high, that means this positive voltage which was transmitted actually remains positive, so that we can make an estimate that this is a positive voltage, and we can make a decision that this represents 1. And also this is true also for the negative side. If the negative voltage remains negative in spite of the noise and distortion present in the signal, uh, so if it remains negative, then we can say that this was 0 was transmitted. Okay. Now, but if the noise limits are very high, in that case, this positive voltage turns into a negative, if that spike in the, if the ripples present in the signal bring the voltage levels to the negative side, but actually it was on the positive side, so we will make a wrong decision in that case. So that's why this line is there. The data can be recovered correctly as long as distortion and the noise are within limits. Okay, so can easily be recovered from the previous signal. So in what happens in the digital communication, so if the voltage remains on the positive side, we can say that it is 1, right, in spite of the presence of the noise and distortion. And if it remains on the negative side, we can say it is 0. And these ones and zeros can further be represented with the baseband signal, right, using a particular digital format. So we can we can estimate ones and zeros, meaning by that whether 1 was transmitted or 0 was transmitted, right. But so the if you look at the immunity level of the digital signals, you will find that even if the noise and the distortion is present, still we are able to make the correct decisions whether 1 was transmitted or 0 was transmitted. But in contrast, the waveform in analog messages is so important, because how the analog signal processing is done, meaning by how the estimation of the analog signal, how the estimation of the information present in the analog signal is made. So in that case, the signal shape is so important in the reception, in estimating the signal, that if the noise and distortion make the shape of the waveform so disturbed that we cannot estimate the information present in the analog signal. So what I want to say is that the immunity level due to noise and distortion are quite low in the analog communication systems rather than in the digital communication system. So that's why I'm saying here that in contrast, the waveform in analog messages is so important, as even a small distortion or interference can cause error in the received signal, right? Because we have to actually extract the information from the analog domain only. We cannot represent this waveform in ones and zeros form, right? So in that case, the shape of the signal becomes very important. So clearly, a digital communication system can better withstand or resist noise and distortion. Thus, it is more immune to noise. So that is why we prefer digital communication over analog communication. And there are more reasons that once we convert the signal into digital form, we can do the processing using the microprocessors or DSP processors or other devices, other VLSI chips, to make the signal a better quality signal. In digital systems, we can use the repeaters also, because once the signal travels through a distance, what happens is the signal loses its strength because of the attenuation and expansion present in the channel. And at certain distance, because if we want to transmit a signal to large distances, what we can do is that we can place repeaters in between the source and the destination, so that the signal strength can be uplifted. So repeater stations are placed along the communication path at distances short enough to ensure that distortion and noise remains within a limit. Because if that exceeds the limits, then we can make incorrect decisions. But if it remains within the limit, digital communication provides that kind of immunity that we can make the correct decision. So the placement of the repeaters is very important along the communication path. So at each repeater station, what happens is the incoming pulses are detected. So the detection is done whether ones or zeros were transmitted. New clean pulses are generated. The new pulses are transmitted to the next repeater station. So going from the next repeater station to the other repeater station, again the noise and the distortion will occur, and we can again regenerate the clean pulses and transmit further. So repeaters actually help in overcoming the effect of noise and distortion. So this process prevents the accumulation of noise and distortion along the path by cleaning the pulses periodically at the repeater station. Now, these are some of the shortcomings of analog communication systems, what we have discussed till now. Based on that, the listing is done here. So in analog system, there is no way to avoid accumulation of noise and distortion along the path, which we can do using the repeaters in the case of a digital communication system, which this is not available um, in the analog communication system. Amplification is of little help because it enhances the signal. Of course, it enhances the signal, but it also enhances the noise in the same proportion. So the signal to noise ratio remains the same. The signal quality can be improved by filtering the signal and then amplifying it. To a certain extent, it can be done. Repeaters used in analog systems basically consist of filters and then amplifiers. They are not regenerative repeaters. Regenerative means we are not regenerating the clean pulses and then transmitting. Of course, there are some kind of filters and amplifiers being used in the analog systems, but the effect is very less as compared to the as compared to the advantages present in the digital communication system. So I end my lecture here, which is based on the distinction between digital communication system and analog communication system, and how the performance of the two systems can be compared. I will continue further with the lecture, with the topics. Thank you so much.